Hello again. So this is my part 3 for semester 1 chapter 1, where in this video we are going to talk about relative atomic mass, isotopic, and also molecular masses. We are also going to have a look at what is actually mass spectroscopy. So entering to the part 3 of this video in here will be what we so-called as the formal lessons for the Stpm, where we are going to make objective of the lessons. So let's have a look at what are the objective of the lessons. At the end of these videos, we hope that you should be able to describe the principle of the mass spectrometer, going to interpret mass spectra in the terms of relative abundance or intensity, isotopes of elements, compounds, and also molecular fragment. We're also going to calculate the relative atomic mass of an element based on the relative abundance of the isotopes from the mass spectrums. Okay? Alright, so as we go to higher levels, you tend to learn some of this technique of analysis, and spectroscopy is one of them. So what is a spectroscopy? A spectroscopy is a technique that gives us ways to investigate the structure of the substance by looking at their spectra. So there are 3 spectroscopy that is used commonly nowadays in research, namely a mass spectroscopy, where the principle of the mass spectroscopy where it makes use of the particles that are bombarded with photons, which knock other electrons out from their particles, making positively charged ions. These ions are isolated by electrical field, forming ion beam, and sorted accordingly to their mass over charge ratio in electromagnetic field surrounding the ionic beams. The next spectroscopy that we are going to look in chapter 2 later is known as atomic spectroscopy. Where atomic spectroscopy is where a gaseous sample is excited by electrical or thermal energy, ultraviolet or visible radiation is given out. This is focused into a beam and then split by a prism or diffraction spreading. The quantized radiation is then viewed through the spectrogram in the form of light emission diagram. And the last type of the spectroscopy, which is not covered in Stpm syllabus, is also known as infrared spectroscopy, where infrared radiation is absorbed, causing atoms at each end of a bond to vibrate relative to each other, like a stretched spring between 2 masses. Energy absorbed by bonds depend on the mass and the bond strength. Hence, quantize the vibration energy where each bond absorbs one band radiations. Okay, so in chapter 1, we are going to have a look at mass spectroscopy. In chapter 2, we are going to have at the atomic spectroscopy. Without further ado, let's begin. Alright, so what is the mass spectroscopy applied at? Mass spectroscopy is a study of interaction between matters and energy source other than electromagnetic radiations. It is used primarily to determine the molecular weight and the molecular formula of the compounds in here. So, the principle of the mass spectroscopy is where sample is first vaporized and then converted into ions, and then separates are detected. So the most common ionization technique involves bombarding the compounds with high energy electrons, which is also known as photons. So for example, if we have a molecules here where it is bombarded with photon energy, it is first ionized to become molecules as shown here with a positively charged ion and even sometimes radicals. So this one is what we call as radicals here. Okay, with an electron knocked out, okay, by this photon energy. Okay, so the resulting species, which is the molecule ion, is positively charged as it has lost electron. Now the dot represents the unpaired electron remaining from an electron pair, where other atoms molecule has been knocked out by the photon. So molecular ion can then form fragments in the form of either ion, molecule, or radicals, which is a neutral species contained in unpaired electrons in here. So some of the examples of how these bonds inside this molecule can be separated. Okay, so through fragmentations of the molecules in here. So sometimes the bond between the more can be broken to a radical form and forms like liqueurs in here, right? So this is how fragmentation can occur. Or you can have a moly, okay, here with a positive charge, and less is formed as radicals, okay, and there might be chances where you have more is separated as a neutral molecule, and then you have liqueurs which has positive and radicals at the same time, and then this molecule can further separated to become liqueurs and also like this in here. So at the end of the day, what does a mass spectroscopy detected? Mass spectroscopy at the end of the day detects only positively charged ions, whereas for example this will be detected here. Right, the rest of them, they will be removed out from the mass spectrometers later. Okay. All right, showing to you in here is some of the compartment of the mass spectrometer. So information about the fragment ions produced is presented in a graph of relative abundance, okay, against mass over charge ratio, which is also known as called as a mass spectrum. So in the form of plural, we call it as a mass spectrum. So typical mass spectrometer has high accuracy and precision to determine the following properties. You can use to determine isotopic mass together with its relative abundance of the isotope's presence, which is later used to calculate relative atomic mass of the substance involved. It can also use to determine the molecular mass of the molecule, and based on the fragments ions produced here, it can be used to deduce the molecular structure of the molecules analyzed. So this is especially applied to many organic molecule studies in the structures in there. The compartment of the mass spectrometers works in a few ways. Okay, so you have what we so-called as ionization chamber, acceleration chamber, deflection chamber, and also detection chamber. So what does each of these chambers do? Let's have a look together in details. So in the ionization chamber, where the sample is ionized, transforming the molecule into a charged ion. So common ionization methods include electrons ionization and electron spray ionization, where the sample is bombarded by a beam of high electrons energy, also known as photon. Okay, now always remember that photon is also a negatively charged electron. So when the electron strikes a neutral, it can be ionized to the molecules that knock out the additional electrons here. So you form M2 plus and also 2E minus. Now this 2E minus indicates that one is coming from the photon itself, okay, and another one is from the molecule itself. So in addition to ionize a molecule, the impact of the energetic electrons may break it apart. So this fragmentation process gives the characteristic of mixture of ion. So the radical cation corresponds to the mass of the original molecule, is also called as the molecular ion. So both charged and uncharged fragments are formed, but only positive charge are detected by the mass spectrometer. Right? So in the acceleration chamber, the positively charged ions, okay, the positively charged ions of mass and charge are accelerated by two oppositely charged plates as they pass through these plates. So this will cause the charged species to move at high speed, which is then channeled to the electromagnetic field. In the deflection chamber, the ion beams enter the detection chamber with a curved portion positioned between the pole and the large magnet ions. So the path of the heavier ions deflect further than the path of the lighter ion. The exact radius of curvature of an ion path depends on the mass over charge ratio symbolized by m over e here. So here are a few examples that I can show you about how does the deflections occur in the deflection chamber. So let's say the path of the deflection, the path of the deflections of the particles inside the deflection chambers is influenced by two factors, namely the mass of the particles and also the charge of the particles. So if let's say you have different mass, which is made of 56 iron plus and 59 iron plus, so how will the deflections of the particles goes by? So it seems that ion with a bigger mass will deflect further. So this is the deflection of iron 56, while this is the deflection of iron 59. If you have particles with different charges, as exemplified by iron 59 plus and iron 59 2 plus, so the one with the smaller charge will deflect further compared to the mass of the ion with a greater charge. So this is the path deflected by iron 59, and this is the path deflected by iron 59 Fe2 plus. So, as a conclusion, greater the mass over charge ratio, further the deflections of the charge species in here. So, let's end up these introductions with the final chamber, which is the detection chamber, where the ions detected are processed in the data collected displaced by the detector, allow for analysis and interpretation in the form of the diagram called as a mass spectra. Below, I'm going to show you multiple examples of the interpretations of the mass spectra. Ready? All right. So let's have a look at the most typical examples, which is made of the neons in here. Right, showing to you in the diagram in here is the mass spectrum for the neon here, right? Okay, as you can see in here, neon consists of three isotopes respectively, namely, since the mass over charge is at 20, 21, and 22, all right, so you shall have this one is Ne20 plus, this one is Ne21 plus, and this is a Ne22 plus. Sorry for that. All right. Okay. So the percentage of abundance given and also the mass of the isotopes given can be eventually used to calculate the relative atomic mass of the neon. Okay, using the formula XA plus YB plus ZC give X plus Y plus Z, where in here X, Y, Z is referring to the relative abundance, whereas the A, B, C in here is referring to the isotopic mass of the particles involved. So in this case, you shall have 20 times 90 plus 20 times 90.592 plus 21 times 0.26 plus 22 times 8.82 divided by 90.92 plus 0.26 plus 8.82, which is then equals to 20.18. So this is how we are going to calculate the relative atomic mass of an element by using the relative isotopic mass and relative abundance in here. Showing to you the next example is chlorine gas. Okay, you ready? Okay, so in chlorine gas, this is the typical mass spectrum of the chlorine gas in here. So where the first two peaks in here is showing chlorine isotopes together with its abundance, and the last three peaks in here represent by the 70, 72, and 74 in here, which is actually coming from the molecules of the chlorines in here. So let's start off with the how to calculate relative atomic mass of the chlorine in here. So showing to you in the first two peaks in here is the isotopes of the chlorine in here. So where you have 35 Cl plus and also 37 Cl plus with the abundance 75 and 25 respectively. So to calculate the relative atomic mass of chlorine, you should have 35 times 75.0 plus 37 times 25.0 over 75.0 plus 25.0. So press your calculator and you will get 35.5. So this is how inside your periodic table, why is it that chlorine can be shown as 35.5 inside your periodic tables. Okay. Now, for the last three peaks in here, 70, 72, and 74, what does they represent by? They are actually the representative of the molecule, because don't forget, chlorine exists naturally as a Cl2 diatomics in here. So when you have 70, so let us just do a little mathematics in here. So what makes up 70 from the chlorine 35 and chlorine 37? So as you can imagine, so 100, the M over E at 70 is made of 35 Cl and 35 Cl respectively in here. So you must put a plus. Okay, so what makes up M over E 72? So there are two chances here. Either you make of 35 Cl, 37 Cl, or it may be another possibility where it is made of 37 Cl and also 35 Cl. Whereas the last 74 is made of 37 Cl and 37 Cl. So how do you get the value of 166.6 and 11.1 in their respective percentage of abundance? So this, you have to play a little bit with probability things. Okay, so let's start from the ratio of the 35 to 37. So as you can see here, since the ratio of 35 to 37 chlorine is 75 to 25, so the simplest ratio of the 75 to 25 is actually 3 to 1. So what does it mean? If let's say you have 4 particles of chlorine, so 3 of it is chlorine 35, and 1 of it is chlorine 37. So you are going to imagine as if now, right, when you are drawing 3 blue pen and 1 red pen. So what is the probability for you to draw 2 times blue pen? So the probability for you to draw 2 times blue pen is 3 over 4 times 3 over 4. So you get 9 over 16. Now, what is the probability for you to first draw 1 blue pen, then 1 red pen? Or 1 red pen, then 1 blue pen. So the probability is 1 over 4 times 3 over 4. Now, because difference order can also be considered here, that is why you multiply by 2. What does it mean? In this case, if you first draw a blue pen, then draw a red pen, at the end of the day, what have you drawn? You still draw a blue and a black and a red, a blue and a red pen in here. So it's just that the difference order. That is why you have to multiply by 2 and you get 6 over 16. And finally, the probability to draw 37 is as if like you draw 2 times of the red pen. So you get 1 over 4 times 1 over 4, you get 1 over 16. And then you multiply each of them by their percentage. Okay, so you get 56.25, 37.5, and 6.25. And this, how you get 166 and 11.1? It is at the end of the day, let's take it if you have divided by 56.25. Then you further multiply again by 100. And that is how you get the 166.6 and 11.1 here. So this is the first example as exemplified by the chlorine here. Second example is bromine. So similar to chlorine, the first 2 peaks, because bromine exists naturally as a diatomic elements also. So the first 2 peaks in here will represent the isotopes of the bromines in here, where the isotopes of the bromine is 79 Br plus and also 81 Br plus. Okay. So you can make use with the abundance multiplied by the isotopic mass to get the relative molecular mass of the bromine. Therefore, you should have 79 times 50.5 plus 81 times 49.5 over 50.5 plus 49.5, you get 79.99. So that is how you are going to determine relative atomic mass of the bromine. Now, what about the last 3 peaks represented by the 50, 100, 50, 160, and 162 in here. So this is actually made of the different combinations of the bromine, because don't forget, at the end of the day, bromine exists as a diatomic molecule. So what makes up M over E 158? So the M over E 158 is made of 79 Br plus. And what makes up M over E and 160? So you have 79 Br, 81 Br. This is the first possibility. Or you have 81 Br, 79 Br plus here. And finally, what makes M over E 162 is 81 Br plus and 81 Br. Okay, so how about you get a peak ratio of 50, 100, and 50 in here? So again, we are going to deal with probability. So since the ratio of the 79 to 81 is 50.5 to 49.5, which is approximately 1 to 1 in here. Okay, so you are now going to imagine if you draw one, if you have two pens, so one is a blue and one is red, where the blue is of course representing 79 Br, while the red representing 81 Br in here. So what is the chances for you to draw 2 times a blue pen? So for you to draw 2 times a blue pen, it is 1 over 2 times 1 over 2, you get 1 over 4. What is the probability for you to draw first blue, then red, or first red, then blue? Again, it's 1 over 2 times 1 over 2, but because you have two chances to get 1 blue and 1 red respectively, so that is why 1 over 2 times 1 over 2 times 2, you get 1 over 2. And then finally, what is the probability for me to draw 2 times red pen? So it's again 1 over 2 times 1 over 2, you get 1 over 4. So in terms of percentage, you get 25 to 50 to 25. If you round up to become 100, that is how you get 50, 100, and 50 in here. So that is how you're going to read the mass spectrums given by the bromine molecules in here. So similar spectra are obtained for organic molecules, but the number of peaks is significantly greater. Now, each peak is due to the particular fragments with certain M over E value. So highest M over E value, this one you must try your best to remember. Highest M over E values usually corresponds to the molecular ions where it provides the information of the molecular mass of the sample involved. And the tallest peak comes from the most stable species is usually used for analysis from these fragment ions in the molecular structure and can be deduced in here. So in the real mass spectrum, you are going to see multiples of a dotted line like this. Most of the time, if you go to the lab, they will ask this lab assistants to remove all these dotted lines. We are calling it as a noise. So this noise can be due to certain isotopes like in this case, hydrogen 2 or carbon 13. So that is what will make a little bit difference in peaks in here. So usually we are going to ignore it. And we take only the highest peak inside the groups in here. So you have 15, 29, 43, 57, 71, 85, and also 114. So now let's say this molecule is obtained with the formula C8H18 in here. So what does M over E, each of these M over E represents in here? So for M over E 15, if you can imagine, so it is the fragment ions from here, which is CH3. Okay, so if it is 29, so you can have CH3, CH2. Okay, there is also a possibility when you have 28, which is made of somewhere in between here, no problem. But let's focus on giving the main peak in here. If 43 is made of CH3, CH2, CH2, which is 43. If it is 57, it is made of CH3, CH2, CH2, CH2. If it is 71, it is made of CH3, CH2, CH2, CH2 plus. 85 is made of CH3, CH2, 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 CH2. And of course, there is also possibility somewhere in between here, which actually I'm the one who forgot to put in between here. So you'll probably get somewhere in between 100 and 99 here, probably. Okay, so this 99 is due to the formations of CH3, CH2, 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 CH2 plus, which is I forget to put inside here. And then finally, for the last peak, which is 114, you shall have the whole molecular mass of these organic compounds involved, which is 114 here. Right? So this helps you, I hope that this helps you to understand how can red fragment ions be produced inside this mass spectrum here. Okay. Okay, so let's have a look at the second examples in here, where you have the haloalkane as exemplified by 1,2-dichloropropane here. Okay, so these are the given fragment ions for the 1,2-dichloropropane, and of course, showing to you in here is the fragments ions for the 1,2-dichloropropane. Okay. So first, we have a look at M over E 15, 28. You have 35 and also 37 here. And then you have 45, 51. You have 63 and 65. You have 77 and 79. And last but not least, you have 112, 114, and 116 here. Okay, so what give all these peaks in here? What are the possibilities that we see in the peaks in here? Okay, so you shall have C15, which is for your information, sorry, before I forget, you should know that most stable carbon is 12 carbon, and then you have 1 hydrogen. So the last information that 35 and 37 shows you the information that it is 35 Cl and also 37 Cl. So you are going to play with a little bit mathematics in here to see what are those peaks is given in here. Okay. So if you have M over E equals to 15, it is given by the fragment ion of the CH3 plus. Okay. Whereas for the 28, so 28, as you can see here, it was probably given by this one. Okay, so you have a C2H4 plus, or simply CH3CH plus. Okay, well, 35 and 37 is given by 35 Cl, 35 Cl and 37 Cl respectively. Okay, and then if you look at here, after you break all these fragment ion, there is also one of these, which is CH2CH3. So CH2Cl here, which gives the two peaks of 45, 49 and 51, where this 49 is represented by CH2Cl35 plus, and also CH237Cl plus here. 63, 65 can be given due to the formations of the CH3Cl in here. So you have CH3CH35Cl plus, and then CH3CH37Cl plus. Whereas 77 and 79 can be probably due to CH3Cl, CH3CH35CH2, which is somewhere around here. I'm going to have a different color so you can see. Okay, so this is it. Okay, so this is given like this. So as you can see, so 77 and 79 is due to the formations of you have CH3, CH35Cl, CH2 plus, and then this 79 is CH3, CH37Cl, CH2 plus in here. And finally, what gives 112, 114, and 116 is the whole molecules of the organic compounds in here, where the 112 is given by CH3, CH35Cl, and then CH3, CH2, CH235Cl plus. Whereas 114, there are two possibilities. We have CH3, CH35Cl, CH237Cl plus. And then another possibility is you have CH3, CH37Cl, CH235Cl plus. And finally, what give 116 is probably due to CH3, CH37Cl, CH2, 37Cl here. So what is the objective in here is, in here you can see that different fragments ions might produce different peaks at the different given mass spectrums in here. So we can eventually use to deduce what is the structure of the 1,2-dichloropropane in here. Okay. So the peak ratio of 112, 114, and 116, as you can see in here, is 9 to 6 to 1, as what I've shown you earlier when we discussed about the Cl2 earlier. Okay. All right. So this is for 1,2-dichloropropane. Then we have last examples, which is made of a carbonyl compound. So we will learn eventually in the semester 3, where we have what we so call as the what we call that isomers. Okay, isomers. Okay, so these are functional isomers where propanol and propanol may have the same functional isomerism. Okay, where in here we use one propanol and one propanol. Now both of them has the same formula of C3H6O. It's just that they present themselves in a different form, where C3H6O may be propanol, C3H6O may be propanol. So I'm going to show you what are the peaks that can probably provided by propanol and propanol. And from these peaks, you can probably see the differences between the two mass spectrums in here. Okay, and there is this one determining peak which will distinguish between propanol and propanol, which will look together. Okay, so of course, the last peak, 58 in here, is indicating the molecular mass of the whole substance in here, where the 58 in propanol, you shall have CH3, CH2, CHO plus, whereas for 58 in the propanol here is CH3, CO, CH3 plus, whereas 15 and 16 is provided by CH3 plus and 16 is provided by O plus here. Now, both of them, you can see how they are producing the CH3 plus and also O plus here, as I highlighted to you in here and in here. So I highlighted in blue colors so far. Okay. Now, what about 27? So for the big 27, I use different color to distinguish it. So for the big M over E 27, it is given by CH2CH3. Okay, so how can you get CH2CH3? So sorry, C2H3. Sorry, C2H3 is this one. Okay, and then this one is this one and this one. Okay. So both of them will be able to give 27, where in 27 you have CH2, CH plus. This 27 is CH2, CH3, sorry, C plus. Okay. Okay, now here comes the determining peak. The major differences between the propanol and propanols lies at the peak of 29 and also 28 here. Whereas 29, there are two possibilities of the peaks that can give 29. So what are the two possibilities in here? You can have CH3, CH2, which is 29, or CHO, which is also made of 29 in here. Okay. So this is the determining peak that will distinguish between propanol and propanol, whereas the 28 in here is given by CO, 28. So this 29, I'm going to write out, is given by CH3, CH2 plus, and then you also have CHO plus, whereas M over E 28 in here is given by CO plus here. Right? So both of them, you cannot have possibility to have this CO plus for propanol, or you cannot have CH2, CH3 for propanol in this case. Okay. Whereas 42 and 43 are given by the same peak. 42 is given by, let's see what the colors. 42 is given by CH3, CH2 CH plus, which is a C3H6, whereas in here you are given by CH3, CH3 plus, and then the 43 is given by CH3CO plus, whereas in here it's given by CH2CO plus in here. Okay, so as I highlighted in here and also in here, yeah, this one. Okay, and with that, that is all the examples that I can share with you. All right, so that is all for our video for the third part, and I'll see you all in the next coming videos in here. Thank you very much.